Alright, this is the final video for relativity, or I should say for the kinematics. So in this one we will be talking about relativity. And it doesn't have to be too difficult for relativity. Basically, you get to choose um, your reference frame. So a choice of a reference frame determines the direction and magnitude of displacement, velocity, and acceleration. So I'll use a couple examples to show this. Think for a moment that you are traveling down the interstate at a constant 55. Ahead of you is a car traveling at 50. So, first off, how fast are you moving relative to the car behind you? And let's say also both cars are traveling north. So both you and the slow car is traveling north. So if you think about it, according to that slow car, when they're looking in the rear view mirror and you're coming up towards them, they see you approaching at 5 miles per hour to the north. How fast is the car ahead of you moving relative to you? So as you are watching this car, how fast is it moving to you? And again, the answer would be 5 miles per hour. However, it would be south, because you would have, to you, that car is approaching you. So when looking at your velocity relative to the earth, that 55 miles per hour, it's relative to the ground. It's relative to the earth. The other car's 50, again, is relative to the earth. So the 5 miles per hour is relative to you or the other car. Now we do have a formula to help us calculate this. The velocity of object A relative to object B equals the velocity of object A relative to the ground plus the velocity of the ground relative to object B. So that is a quick little formula that we can use. Something special about this, if you reverse those letters, it introduces a negative sign. So let's go back and let's take a look at these. How fast are you moving relative to the car ahead? So I'm going to say that you are object A, the car ahead is object B. So when we take a look at our formula, VAB equals, okay, first one, object A relative to the ground. Okay, well that's 55 miles per hour. And that's to the north. Plus the ground versus object B. Okay, this is where we have to think. Object B, the car ahead is moving at 55 miles per hour. 50, I'm sorry. The car ahead is moving at 50 miles per hour north. So the ground must be moving 50 miles per hour to the south. So if the car was stationary, think about the ground moving underneath of it. So with that being said, this should be negative 50 miles per hour, because the ground, if you think about it, the ground is moving to the south, not to the north. So if we say everything north is positive, everything to the south would be negative. The ground is moving to the south, so we have that negative. So again, we get a positive 5 miles per hour, which means that it's 5 miles per hour to the north. Okay, how fast is the car ahead of you moving relative to you? Okay, so again, well, this time I'm going to make the car moving ahead of you A. I'm going to make you B. So the car ahead relative to you would equal, okay, so A comma G. So the car A, the car ahead of you, would be moving 50 relative to the ground, so it'd be going north, so it's going to be positive. Now the ground versus, okay, again, if you think about it, if you're stationary, the ground is moving underneath of you at 55 miles per hour. So we would have to have a negative 55 because the ground is moving to the south. So that gives us a negative 5 miles per hour. And again, negative means south. All right, let's look at another example. Something a little more complicated. We have a boat heading north across a wide river with a velocity of 10 kilometers per hour relative to the water. The river has a uniform velocity of 5 kilometers per hour east. Determine the boat's velocity with respect to an observer on the shore. So let's see if we can get a visual of this. So here is the river. Here is the boat. The boat is trying to move this way. The water is moving this way. So if I have north and east. So if you think about it, what path would this boat actually take? You know, if someone is standing right here on shore watching this boat, they're not going to see the boat go straight across the river. The boat's going to be carried with the current of the river a little bit. They're going to see the boat make a diagonal, if you will. And the speed's going to be different as well. They're not going to observe the boat traveling at 10 kilometers per hour. Probably a little faster since the current's carrying the boat. So let's set up our equation then. The velocity of the boat with respect to the observer would be equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the observer. Okay, so the velocity of the boat with respect to water was 10 kilometers per hour, and that was north, plus the water is moving at 5 kilometers per hour east. We can't add those two numbers together. They're going in different directions. But we can do some vector analysis, and we can use vectors to help us add this. So the boat will be traveling at 10 kilometers per hour north, and the water is traveling at 5 kilometers per hour east. That sets up a right triangle, so we can calculate the velocity using the Pythagorean theorem, and we can use inverse tangent to calculate the angle. So the velocity of the boat with respect to the observer, then if we use the Pythagorean theorem, we get 11.2 kilometers per hour at an angle, and if I do inverse tangent, so this would equal inverse tangent of opposite over adjacent. It gives me an angle of 26.6, and that angle is east of north. So what the person on the shore would see is not a boat traveling at 10 kilometers per hour directly north. They would see a boat traveling at 11.2 kilometers per hour at an angle. Okay, well this concludes our video, and it concludes our unit notes on kinematics.